So let's see if this will go. I believe it's recording. All right, so in any case, what I want to do, as I said, I want to kind of talk a little bit about this class and how it came to be what it is. It might seem a little bit different from other math classes you've taken, but I guarantee you it is math and it's the best kind. So I want to compare a little bit math education in the US versus some other countries, and compare the approach to math that we're going to use in this course as compared to what you might be used to doing that might not be your experience. Everybody's coming from a different place. So I don't know exactly what your experience is. I taught high school for a while. I know what usually happens in high school, and I know what happens in a lot of other math classes here. But we're working to make math more useful for you in the 21st century. We're working to make it more comprehensible as opposed to just a bunch of stuff. You write some formulas and plug in some numbers and boom, you're done, because that makes it very unfun. So just as a comparison, TIMS, which is a research of science and math education, they did some recordings of middle school classes, 8th grade classes in Germany, Japan, and the United States. And they're education researchers looking for what sorts of activities were going on in class, what sorts of questions were being posed to the students, what the students were being asked to do. And they categorized these into like high-level activities, medium-level, kind of moderate activities, and low-level activities. So, for instance, like a high-level activity might be where you have to research something or figure out a new rule or look for a pattern and describe it to somebody else. A medium-level activity might just be doing like advanced story problems. So like, here's a problem. It's maybe like some ones you've seen before, but it's a little tricky. The low-level ones are like worksheet, like, you know, solve these 30 equations by subtracting and dividing. Kind of boring stuff. So in the German classrooms, and as it says, they're strict of like nobody knew it while they're looking at it what country this was. But in the German classrooms, we had kind of an even split between the 3 levels of activities. Whether it's like, you know, just involve the students a lot, involve the students a little, give them some low-level practice, give them some moderate-level questions, give them some challenges. So, all right, then Japan, kind of similar. A little bit less on the low and more in the medium, a little shift there. So a lot more of that medium level, slight challenge sort of questions and slightly harder level of difficulty activities to finish. A little less on the low, but about the same on the high end. Now, for US classrooms, I don't know what your experience was. I know I had a lot of do this worksheet as fast as you can when you're done, raise your hand. That, who did that? Yeah, I did that. Pretty good at it, not particularly useful. Nobody really, well, actually I get to do it kind of sometimes when I have to try to calculate things while I'm standing in front of you, but not very many people really have to do that. Here's the average over US 8th grade classrooms. Yeah, so not particularly good. If your 8th grade class seemed kind of like your 9th grade class, but 9th grade was just a little bit harder, maybe it wouldn't quite fit into that same category, but 11th and 12th grade, with any luck, maybe you did some more challenging things by the time you were finishing high school. Maybe this is your second year here. Maybe last year, I hope, was a little bit more challenging. I hope in general that college is more challenging than high school, because if it isn't, then why are you paying money? Why are you doing this? How is this helping you reach your goals? So I want to help you reach your goals. I don't just want to be a textbook that spews the same stuff at you that you could have read on your own. So obviously, we're not going to be doing necessarily what's common among US classrooms, certainly not what's common in 8th grade classrooms, because we're well past 8th grade. But the moral of this story is comparing US education standards of what's normal in this country to what's normal in other countries, it's not necessarily good what's been going on here. Not all of you are from the US, not all of you went to school in the US, even if it's where you're from. But I hope that maybe a wide variety of backgrounds from you. Some of you have you're in this class already. Some of you probably had some of the better teachers in middle school and high school that got you to this point, so you're actually still interested in this, you want to go to school. So I'm guessing you're among the top. I want to keep you there, I want to push you, I want to make you go farther, I want to help you get past any hurdles that you have, any misunderstandings that you might have acquired over time. So This class might be different from ones you've seen in the past. Maybe it'll be similar. I hope it's similar because we've worked really hard to make this useful for you. And if you've had very useful, meaningful classes in the past, then I hope this is like that. But why we need to make changes from what was done in the past, because in the past, different things were needed. In the past, people learn calculus to get jobs are required. They do lots of computing. Did you ever see the movie Hidden Figures? Like the job title literally was computer. That's not a job title anymore. There's computer programmer, and that's what they transferred to in that movie. But yeah, we don't need you to do the computations. We have computers that can take care of that end of it. A lot of the simpler level, that lower level math activities that were spent a lot of time on in US classrooms, that's mostly stuff, computers can take care of that. I want you to know how to do some of these, but that's not what we're gonna focus on. In the past, you need to be able to do these things really quickly, like whether it's do trig really fast while you're flying in the back of a bomber in World War II or whatever. We're not gonna make you flip through books and get angles as fast as you can based on wind speed estimates while you're about ready to kill people in action. No, that's not what we're doing. We've got computers that take care of all of that stuff now. So the people that were learning math in the past needed to learn it to be the computer. We want you to be a step above that because we've got the computers now. So whether it's programming the computers or setting up the people who are going to be programming those, or just understanding the background behind all of that, that's what we're going to focus on. So today, as I said, computers can do things much faster than people can. For the most part, there's probably a couple people that you've seen videos of them someplace or another doing crazy things. But computers still can't completely take in a situation around them and figure out what to do. Like there's a lot of AI that's getting close to that, but we still need people that need to design that, make it better, etc. We need people to translate a situation into the mathematics that's behind it and analyze that and figure out what's going to happen, figure out what needs to happen. So, in other words, the people that are using calculus today in the sorts of jobs that are available today where calculus is a requirement, you're not going to be sitting there doing computations because the computations aspect, the manipulating symbols and moving them around, computers do that. We need you to formulate the mathematics that is the earlier step in that process. So that used to be the more rare job, now that's the one that we need. So what we are not going to be doing is a lot of, sorry about that, speedy worksheets. There is going to be a brief respite in the middle of the class where it's, let's work on these rules. Derivatives, if you've taken calculus before, there's a bunch of shortcut rules to learning how to find them. That's a minor component of this class. It's good to have those in the back of your head. It's like the equivalent of the learn your addition table section of arithmetic. Nice to know these things so you can do them quickly and not have to worry about it, but it's not the most important part, and it's a small portion of your course grade. So for the most part, though, we're not going to just be doing memorization and repetition of the same sort of thing repeatedly. None of this just, this is one of those kind of problems, and you just do the exact same 2 or 3 steps every time. Also, though, don't take this as if I don't say the words just right, then I don't get credit. There's a lot of different ways that I'll phrase things during class. A part of your course is recitation. In recitation, a lot of what you'll be doing is getting more of a chance to discuss things. This is a rather large setting for a discussion. So you'll get a chance to discuss things more in a person-to-person discussion with your classmates there. We'll do some of that in here. With your discussion leaders, your recitation leaders, in order to work on saying precisely what it is that you mean. Because changing words, sometimes people can misunderstand what you mean by things. So it's just as important in math to say what you mean and to say it clearly so other people can understand you as it is in any other subject area. But that's one of those things that's kind of passed over a lot in earlier classes just because let's just get the numbers right. Let's just get the answer. So what I do want you to do is a lot of thinking. Thinking about why, as we're going through a rather long process of developing something that we'll use for the rest of the semester, why it is that it's important, how the different pieces are related, what are the components of this expression doing, what does each one mean? calculus is really a generalization of algebra. It's just the same sorts of concepts you did in algebra. We're generalizing it, making it more complex by thinking about larger scope and smaller scope sorts of aspects to things. So we're going to be analyzing in different situations that are presented the relationships between a couple of different quantities, a couple of different things that we can measure, so like measuring whether it's time and distance, or whether it's elevation and temperature, lots of different things that we can see how they're interrelated with one another. And the main idea, though, for the calculus is that all of the things that we're doing are focused around one key relationship. It's called the fundamental theorem of calculus. And we're going to be starting with working on that as early as, let's see, a third of the way through the class. We'll already be to this fundamental idea that relates all of the pieces, and then the rest of the class after that we'll be working on how do we understand this, how can we use this once we get some basic relationship styles down. Once we figure out some basic ways that quantities are related to one another, we can use that idea, which I don't know if you remember in maybe an algebra class, the fundamental theorem of algebra. Basically, it says that equations have solutions. It's like, great, that's fun. And we're going to use, that's probably the extent to which you use it. Great, there's answers. X squared, there's going to be 2 answers. X cubed, there's going to be 3 answers. They might be the same, they might be imaginary, but there's answers. So in any case, the fundamental theorem of calculus, we're going to weave it into what we do a lot more so than just it's thrown on at the end. So I hope that you see this theorem that relates how things change to how much of something we have back and forth, whether it's a physical quantity like piles of dirt over time, or whether it's something more like how much time I have based on something. It doesn't have to be physical quantities that I'm weighing and measuring in that sense. It could be things related to time where I just measure its passing, see something elapsing. But in any case, I did want to show you what's been going on with this class. We started being funded by the National Science Foundation in 2016 to bring this program to more students at ASU. Prior to that, it was just an experimental class, but we're past experimental phase 2. We're doing really well. So what was done is we compared the outcomes of people who are taking this course and using the materials and having the same requirements as you're going to have to students that take a more traditional calculus course at ASU. And during the first year, the study was compared to engineering calculus, MAT265, if you have any friends that are taking that. And so there's a lot of numbers and statistics up here, but if you can see in the first table there, that table 2, there's another one earlier in the thing that I snipped this from, but that ENG is engineering calculus, and DIR stands for DIRAC, which is developing and investigating a rigorous approach to conceptual calculus, and that's written all over the place, but that is our grant title. And you can see there are more people in this DIRAC during that first year. There is a weird, before the semester began, there's a pretest and a post-test. So this pretest, that's the mean score that people had on this pretest. Just about 3 for engineering and 3.7 for DIRAC out of, I think it was 20-something questions. This is how much you know about calculus before you've taken calculus, so obviously expect the numbers to be low. But for unknown reasons, because you're all smarter for taking this one, people that take this calculus started out a little bit ahead of the engineering calculus. You can see the pretest mean, and then skip a column, and there's the post with that same mu symbol up here, post-test mean. And those are both higher. Still the DIRAC is higher than the engineering, but you can see, and it's easier to see in table 3, the gain over the course of the semester was about 1.4 for people in engineering calculus versus 3.4 concepts for DIRAC calculus, which is based on the setup of this test that's highly statistically significant, meaning massive, massive amounts more gain from taking this sort of class in understanding of the concept of calculus than in other more traditional classes. Also, this is a little snippet again, interesting. Now, 21% of engineering calculus students had a negative score over this, meaning they did worse on the post-test than the pretest. Only 4% of people in this class did. Still kind of weird, but that happens when you, at some point in time, are guessing. Didn't know what to do. But in any case, I did want to share that. This is from a couple of years ago. after the 2016-2017 school year, these results were out. So in any case, that's just, the purpose for having this class was to make calculus more meaningful for students and to help you through it. And so far as we've been studying, it has been working. So, what we want to do, we want to rely on your understanding of the concepts involved to be able to put them together into larger groups of ideas and to solve more complex problems, including things that you haven't encountered anything like before, just by thinking about the underlying relationships between the things in there. So it's not going to be a bunch of, here's a worksheet with 12 questions, they're all kind of the same with different numbers, go. Even if they're story problems, that's very boring, and it just means you figure out how to do one specific type of thing and you can repeat it, which is good, but isn't the goal of this class. We want you to understand all the relationships and show that by continually being able to understand and approach new problems, including why you did something the way you did and somebody else maybe did it a completely different way. Justify what it is that you've done, why it works, why something else maybe wouldn't work, and those sorts of things, like the why is this okay, why is this better? It's sort of judgment calls on looking at things. Why would one thing be more efficient than another? Some good things to think about, not just get an answer, circle it, done. So in that frame of mind, we will have office hours starting next week. We're all just still getting organized and everybody's starting up classes, I know. But when you come to office hours or for tutoring, just be prepared. If you ask a question, you might be asked questions in return to try to make you think about how to come up with the answer. But by doing that, although it takes a little bit longer, we hope that the idea is that you will understand and can repeat this later, can think about that later. The next time you have a question, ask yourself, well, why would I need to do that? Why should this be the next step? Or as you're going through something, if you just did something because, like, why am I doing this? Does this make sense to do now? So just creating more critical thinking about the use of mathematics as opposed to just do it because this is a rule and that's the end. So in any case, you will be challenged, I hope, in this class, but I hope that the payoff for that extra work beyond maybe what you're used to or what you maybe were expecting is good. I hope it pays off well for you. And that going on in your future classes, whether it's in your additional math classes or the ones for which this was a prerequisite, I hope that you find that path that we've taken through here helps you in the future, because if it doesn't, then we're doing it wrong. All right, so let me show you one of the programs we're going to be using in here. And I ask you to try to download this before class. It's called Graphing Calculator. I know some of you have had difficulties. It is a program, so you can't download it onto a Chromebook, but a Mac or Windows, and I think even Linux works because it can be altered to work like other things. If you don't have a laptop or if you only have a Chromebook, you will be able to access this program at the campus computing sites around, including in the Math Tutor Center. They have this installed there. It's a free program for you to use because of the grant that we have. You can use it on one computer. So just, there's the license information and serial number or whatever it's stated in the one of the two announcements that is in Canvas. But if you did get it installed properly and open it, it looks like this, which is very boring. It's like, huh, what is this? So this little purple icon there, this is what's called a command line. You'll see actually in Canvas, there are not very many things showing just yet in Canvas. They'll be added to throughout the semester, but a couple of them are keyboard shortcuts for GC on Mac and on PC. So you'll be having an assignment to look at in the very near future related to your recitation that is working through just how do I type in this? How do I get GC to do that? But GC is more than a handheld graphing calculator. It does do graphs and it does computations. It also does a lot of other things. And I just want to show you the basics of some of the things that you can do on a handheld graphing calculator, for instance. If I do something like 3 plus 2, I can do that on any calculator. As you're doing computations, it shows you the result over to the side. So if I change it, it has a new result without having to hit enter or something in between. I can add exponents on here, and it looks like exponents. So now I've got 3 plus 21 squared, and so forth. One of the things that's nice about this, not for necessarily just arithmetic, but it does work in the sense that a word processor does. You can copy and paste. So I can copy this, like Control-C or Command-C, depending on what kind of computer you've got, and paste it later in a different expression. So if you have a big, long expression, you don't have to write it twice. You can copy and paste. Or from here, another thing I can do, if I have that all highlighted and I just hit one parenthesis key, like the left parenthesis, puts it all in parentheses, and then I can do something else to that. So it's sort of more flexible than standard computer or standard handheld calculators are, just in the basic sense of this. Now, if you want to have a new command line, hit Command and Enter, or Control and Enter, and then you can have another line that looks like this. Now, the color of this is really only relevant to either help you not get dizzy looking down a page of a lot of them, or when you're doing graphs. So you can have this graph for you. If I say y equals x squared, this graph button appears, and it'll show me a graph. And you can drag the graph around, say, oh, I want that to be in the center. You can also make it appear next to your text instead of under it, if that's more convenient for your screen size or just what you're trying to do. You can zoom in and out just with a click. Shifting and clicking, you can zoom in on a particular area of the graph. So I can look at this, and well, one thing that we're going to talk about a lot in this class, oops, if I can drag this. This was a parabola, right? Now it looks like a straight line. Parabolas and lots of other graph types or lots of other function relationships, when you zoom in on them, they don't really look that much different from one another. If you zoom in close enough on a lot of things, it looks pretty much like a straight line. Now, straight lines have a lot of nice properties. Constant rate of change, the slope, as you might have talked about it in many other classes, the slope of the line. And say, oh, it's what angle it's going at. Well, that's what the graph is doing. But if I talk about an equation like y equals 2x plus 6, that 2 tells me a lot of things, but as x changes, y changes at a rate that's twice as much. So if I change x by 1, y changes by 2. If I change x by 9,000, y changes by 18,000. It's always twice as much because of that 2 that's in there, no matter how much. For any small change in x, y changes by twice as much. Now, if I'm looking at something that wasn't really a straight line, but looking at it close enough gives me a straight line, I can talk about the rate of change of this graph, like the steepness of it. Now I'm zoomed in really close. From left to right here, this is like, you probably can't see this, but this is 2.748 and 2.749. So left to right here, this is 1,000th of a unit. But going over this 1,000th of a unit, that looks fairly much like a straight line. I could compute the ratio between the changes in the output and input, whatever this might represent. It was a parabola to start with, but looking at this, I say, well, in this small section here, this seems to have that sort of linear look to it. It looks like a straight line. It looks like something that has this constant rate of change, where there's a ratio between changing my input, whatever that might represent, and changing my output. So looking here, let's see, I'm going to say this is, well, we could calculate this. Let's see, going from that spot, and by the way, if you click right on the graph, it tells you the coordinate points, and you can even drag this along and it sticks to the graph. So you can find a couple of coordinate points. You could compare more precisely the change in the vertical and horizontal components of this, meaning the change in the x variable's value and the change in the y variable's value. And we could come up with a slope for this and compare it in different intervals. But this is what we're going to build to over the course of the whole semester, is that basically there are a lot of sorts of functions for which if you zoom in on them close enough, they look like straight lines. And we can use the properties that straight lines have, this constant rate of change, to tell me, well, if I have a rate that's constant, I can project what happens because of that. And if I know in the other sense what happens because of that, right here we have the end result, I can find a rate based on that. And whatever rate I get only applies to small moments at a time, small little intervals of x at a time. But that's good enough in reality to be able to put together pieces of information like that tell me if I know how much of something I have, I can figure out how fast it's changing. If I know how much of something I have and see that amount changing, I can find a rate of change for that. As long as it's certain types like this that are relatively, when one changes, there's not a sudden gap or something crazy that happens in the corresponding output variable, the y variable. Or other way around, if you know a rate of change, like if I told you how fast I was driving, you could tell me how long it would take me to drive a certain distance. But if my speed changed, as long as you had a lot of different pieces of information, my speed at various points in time, you could still make a pretty good estimate about how long it took me to drive 200 miles or whatever it is. So varying rates of change, as long as they vary nicely, let's put it kind of vague like that for now, as long as these rates of change nicely, we can estimate what happens because of them using nice regular sorts of math properties that we use with linear equations. So, all right, so GC, we can do graphs, we can do arithmetic. You can even do things like write in some text. So if you've been working on computer programming at any point, you want to make comments on something. So the line above was used to demonstrate constant rate of change can be seen in a quadratic function graph. And so you can comment on what it is that you're typing. So over the course of the semester, you'll actually be doing a lot of assignments in GC. Your recitation leaders will post assignments that are GC files that have questions written in text in there, as well as some instructions. Make GC graph this, or get your picture to look like, and then you'll see it like a picture off to the side. Put in some formulas. It's just you get to learn how to type the specific math that you need, and it's not a programming language. You just get to type in things like you would have to explain them if it were a textbook to make this appear, to make that appear. So let me clear out this graph. I don't need this stuff anymore. I'm just going to open up a new window. Easier than deleting stuff or resuming anything. But so for instance, you've seen functions and function notation before. If I define a function, something like f of x equals x squared minus 5. I've just defined what function f of x is. If I wanted you to compute a value for f of 6, all you have to do is type it, and it does it. By defining your function, you've just made sure that within this window, GC knows what you're talking about if you use f. And you don't have to have you don't have to do a computation. Just f of something refers to a result from using the previous function. If I type this f of 6 without the line up above it, it would just kind of give you computer gibberish like, well, it doesn't know what this is, so it'll assume it's a 1 and just do 1 times 6 and doesn't know what you're talking about. But if you've defined a function, you can have GC do computations with it. You can have it be graphed. So for instance, if I wanted to graph on the y-axis the output values from this function, the dependent variable values, I can type y equals f of x. See that graph button appear down at the bottom there? And maybe I don't want to graph the whole thing. Maybe I just want to graph it between 0 and 3. So I can tell it to graph the function f of x, graph as the y values, the output from f of x, where x varies from 0 to 3. And I can zoom out. There's also buttons here for quick zoom in, zoom out. You can see, oh, well, there's that graph. And you type it just expressions exactly as you'd see in like any math textbook, the way that they appear nicely. You don't have to have any fancy, like go to a menu and select a weird symbol to indicate that you want to do a limited domain. No, just type in what you want to see. If it's legal looking math, then it'll appear for you. So in any case, there's a lot of things it will do with GC, and you'll learn about some of those in your first recitation, which those are next week, Monday and Wednesday. You have your first recitations. I did want to introduce Barbara is one of your recitation leaders, and Axel in the back is the other recitation leader for you. So you're going to see one of those two once weekly in recitation, in addition to any other time. They'll be in here quite a bit at the beginning of the semester, and then kind of sharing duties in here later on and taking care of more. They are going to have office hours. But let me explain a little bit about how your grade works in the class, how Canvas works for the class, some of the nuts and bolts logistics of the course, so you kind of understand what it is that we're going to be doing on a daily basis, and then we'll get back to some more math. All right, so let me open up Canvas. I'm already in Canvas. Sorry about that. There we go. Slow internet today. So I'm going to have to shrink this down a little bit. All right, so apologize, display is all the wrong size. So on our Canvas homepage, if I can, no, it's still too big. There we go. On the Canvas homepage, you'll see announcements at the top, and then modules down below. I don't know if I can get this to show. There it is. Just what you'll see. There's a lot of extra stuff that I get to see that you don't have to worry about. There you go. So you'll see announcements at the top, and then there's this introductory information in the first module here. Can I scoot this over? It won't even let me scoot this over. I apologize. I have to work on getting this display settings a little bit better for us. There's a link to the syllabus here. I just want to point out a couple of things in that, but I'll let you read it on your own. Here's a link to our text. Our text is free and online, and the authors of this textbook are here on campus. It's not like a mystery person that lives on the moon or anything like that. Here's a link, as I said, to our YouTube channel or the playlist from class. After class today, it'll take a little while because processing videos takes a while. But I'll upload the newest video from class there. Probably don't need to see that one if you were here, but that's where they're going to be in any case. Check to make sure that you can click this, follow it, it all shows up. If it's messed up, let me know. I try to test everything out, but and your homework site is iMathAS. It's free. If you registered sometime between 5 p.m. yesterday and now, you might not yet be in the system, but as soon as class is over, I will go and look for new registrants to the class to make sure that you're in that system. If you have been registered already prior to yesterday evening, you should already be in the MathAS system. To log in, you just use your ASU right, and there's a fake password that's in there. You can leave it there if you want, but that's in this introductory announcement. So make sure you read that. There will be office hours posted soon. I just wanted to wait till I have a few more of them, but this link, there'll be a list of office hours, not just for me, but for me, our two recitation leaders, as well as there's another MAT270 lecture that is using the same materials. Their lecture and two recitation leaders for them as well. There will also be people who have gone through the calculus sequence and are tutors that work in the tutoring lab that are good at understanding what your questions might be, are experienced in explaining things that you might have questions about so that you can ask your own questions, but they also know how to ask questions back at you and make you think about it. So in the tutoring lab, there's a special area for MAT270 and 271. They're right next to one another. But I'll have all the office hours here. There's a little bit every day. They're mostly in the mornings for the lecturers and recitation leaders because all of us have lecture and recitation in the afternoons. There will be more afternoon and evening hours in the tutoring center and some of the other locations on campus. The Math Tutoring Center is Wexler 116. It's near that coffee shop that's outside, right over. Yeah, that direction, right across the sidewalk from here. So let's see, other things. So right now, and I just posted this right before class, all this here for module 1, our first set of stuff before we come to our first test. All the materials that we hand out in class that you get from recitation are going to be in this area. There's a separate section for specific recitation formula, documents, activities, etc. But this link right here, week 1, half week, I actually filled it out before I came to class today with a list of things that you should do before the next time that we see one another. So before class on Tuesday, which is our next lecture, there are some things here. make sure you can log in and use iMathAS. There are actually 2 assignments in it that are due by Monday night. They are kind of review and introductory material. It's not about calculus. It's not random hard math that you've never seen before that you're going to have to come up with. There are some questions about understanding the meaning of and computations with large numbers and converting between different types of units, just kind of background pre-algebra and algebra sorts of things, including scientific notation. And then the other one is just about using iMathAS in general, and there's just some practice questions that make a graph that looks like this, and it's just trying to follow the directions, or how to answer multi-answer questions, like select all that apply, those sorts of things, just so you get the gist of how the system itself works. So assignment 0 is the kind of intro to how to use iMathAS. Assignment 1 is about, well, a lot of items from chapter 1. So the focus of our class is going to be chapters 3 through 7. Chapters 1 and 2 are introductory type material, pre-calculus. Chapter 1 is all about large number scientific notation, units and conversions, and how to understand what it means to convert between units, as well as a brief introduction to constant rate of change, which you have seen before, but we're going to talk about it maybe in a different way than you have before. Those sorts of questions you won't see yet in the homework. Chapter 2 is all about trigonometry, which we'll touch on trigonometry throughout the class, and that'll be a source for kind of review of some topics from trigonometry if it's been a while since you thought about cosecant and things like that. So let's see. So things to do over the weekend: log in and use iMathAS. Be sure you've successfully downloaded GC. You'll be using it in recitation next week. And then read through the text. So the preface for students in chapter 1, including section 1.5, it starts at 1.0 through 1.5. The first one is tips on installing GC, and also a link to install it if you need. There's several sections, but let me just take you to the textbook then. So I have it bookmarked. You can bookmark it. It's not like one of these secret links where you have to follow the link and you can't bookmark it yourself. But our textbook is just following this. And there's a description of the project and grants and things like that at the beginning. There's a preface for students, instructors, and here's chapter 1. So this is what you're going to be looking at over the weekend. You can see that, some installing graphing calculator. Okay, if you already did that, you're fine. You don't have to read that. And some of these are very short sections. Some are longer sections. But there are some questions in there at the end of these sections, which are the same as some of the questions that you'll see in the iMathAS homework. But this, like I said, chapter 1 and chapter 2 are kind of review and background information. And so chapter 1, there's an assignment covering the background information from that up through section 1.4. Within that, one of the 2 iMathAS assignments. Chapter 2 is trig. Chapter 3 is where we're actually going to spend the majority of our module 1 time. The first test covers chapters 3 and 4. 4 is very short, comparatively speaking. And the first 2 sections of chapter 5. So our first test, and that's going to be in about 6 weeks. After that, we'll go up through chapter 7 and have a second test after these highlighted links finish. In between those 2 tests, there'll be something called your mastery exam, which is the one I described. It's the kind of, make sure you know all these rules and can apply them, but it's the kind of boring part of calculus. It's the multiplication tables part of calculus. Just learn the rules, make sure you can do them in any situation, and then we're good to go. But not story problems. It's just do this, do this, do this, like do an operation. So the final exam covers chapters 1 through 6, or 1 through 7, I should say, with just a few little bits from chapter 2. Chapter 2 is pre-calc sorts of stuff, trigonometry. But let me go back to, no, not from here. Just start this over. My view is nicer. It's not got all that pink stuff on it. So this daily information, and there'll be like week 2, that will be next week. After class on Tuesday next week, I'll give you some things to think about and do before our next class on Thursday of next week and so forth. So it'll be updated after every lecture. once there are handouts, they'll be listed there, but everything else is right up at the top. Now, the iMathAS, when you create your login following the directions, you'll see you don't have to do this and enroll in a new class. You'll see the class already. It'll just look like this, only it'll say courses you're taking, not courses you're teaching. And you can see there's a calendar in there. On this calendar are not everything that we do in class, but all the iMathAS assignments are listed in here and their due dates. And you see they're kind of scattered. Every several days there'll be something due in there. So you don't get to like sit back and wait for 2 weeks before you go and do like 10,000 assignments at once. There's a little bit as we go along, like a couple times a week, generally speaking, until we're coming up to a test where you're going to be working on assignments. And I said homework 0 and 1 are due on Monday next week. What this color coding is, the blue things are events and holidays, just kind of, they're not assignments. The ones that are green and yellow right now, those are assignments. Green means it's a ways off, yellow means it's due sooner. They just picked this one to be due slightly sooner than that one. If something's due tomorrow, it'll be red, kind of like stoplight warning, like, hey, pay attention to this, do this now. It doesn't, yellow and green don't mean something different in terms of your grade. And there's some information about rounding and how to make sure you're not getting marked off for just entering your answers incorrectly on here. So make sure you read the announcements that are in there. But let's see. The other thing I wanted to show you just briefly, how your grade is determined in class, and that is in your syllabus. And I'll just download it from here. It's faster than. All right, so lots of details. Make sure you read it, dates and whatnot. Here's where your grade comes from. So the homework that's in iMathAS is 9% of your grade. There'll be little online quizzes every once in a while in here or in recitation that are just a small little bit because you haven't had time to study and prepare and that sort of thing. So just little small parts of your grade, 1% total for all of them. So don't worry about it, but don't just skip them. We give you these to kind of see if you're on track, to see if you understood what we did so we can get some instant feedback from that as to how the lesson is going when it just happened. But I don't want it to really impact your grade alert, so it's 1%. We will have written quizzes about, during the semester, 8 or 9 of them in class. And these are you'll know what's coming on it. And it's going to be on Thursday, sometime during class, sometimes at the beginning of class, sometimes at the end of class. It'll be generally on Thursdays. Not every week, obviously, as there's only 8 or 9 in the semester, but many weeks when there aren't tests, we will have quizzes that are like one sheet of paper sort of quizzes, but you can use your notes, just not your neighbors, those sorts of things. So if you have notes written down, or it can be computerized notes, but it just has to be notes, not browsing the web sort of information. Recitation assignments. In recitation, you'll be doing GC assignments, you'll be doing other written assignments. Those are a part of your grade. We have 2 main tests in the middle of the semester, whether you want to call them midterms or whatever you want to call them, after about the first 6 weeks, after about another 7 weeks. And those are each 15% of your grade. There's a mastery test that's 10% of your grade that's in between those 2 tests. It's a different format. It's these 2 exams, number 1 and 2, those are actually all multiple choice, which might seem weird to you, but the class isn't based on computation. So it's an understanding what is meant by different expressions, which would be a proper expression to represent this, those sorts of things. So it's really about interpreting and being able to come up with how this can be done. So it's not computation. In fact, for the first test, you're not allowed a calculator. There isn't really any computation anyway. For the second test, we'll allow a calculator because there are some minor computation issues with some of the topics we'll be talking about where you might have to like divide by square root of 2 or something, which is not a do by hand sort of thing. But just minor computations. You don't go out and buy a fancy graphing calculator. You can get by as long as it has add, subtract, multiply, divide, and a square root button. You can do it on a calculator. Derivative mastery exam, as I said, 10% in your final exam on Tuesday, December 10th at night. Maybe in here, maybe not. I'll let you know what the room is for that. I find out usually about the start of November, but that's 25% of your grade. And the final exam, like the 2 midterm exams that aren't the mastery test, it's also multiple choice. So in any case, please read through the syllabus. There's a schedule of events, and you can see that where the tests fall in this, as well as holidays. We don't have Monday classes, but some of you have Monday recitations. There are a few times during the semester, so that everybody has the same number of recitations. There'll be a few times during the semester that those of you with Wednesday recitations won't have recitation because the Monday people didn't or won't the next week. So just, I'll try to remind you of those sorts of things in class. Labor Day is one of those that's coming up in the near future, but we'll just kind of switch around, and it'll actually end up being right before your first test that we'll be skipping a recitation. So everybody has an equal number of recitations between tests in the beginning of the class. All right, so let's get back to math. This is boring. We need some logistics and organization, but it's not what I like to talk about. All right, so let me get rid of all this stuff and get back to the mathematics of rate of change. So section 1.5 in your textbook is where we start talking about rates of change. And to some extent, I expect that it should be a review of some concepts. But what I want to do is start out slowly so that we have a common vocabulary we can use, so that we understand what one another are talking about, so we have a chance to work out how to say things precisely, and also to come up with a variety of ways to say things. Because, like I said, you don't have to say things one particular way for it to be right, but we do want to make sure that however you're trying to explain things, whether it's in symbols or in words, that you're being exact in your language, that you're not leaving things kind of half undefined so that someone can misinterpret what you meant. But let's just start with change and rates of change. So some notation that I want to introduce is something you may or may not have seen before. But just as an example, suppose that your phone states that your current programs take up 7.8 gigabytes of space. You download a new app that uses 0.5 gigabytes. How much space is now used by the program? Now, math-wise, that's a simple question, and I hope that you know the number answer to this. But let's talk about some symbols we can use so that we can use the same concepts in a variety of situations, and we're going to actually use some of this throughout the entire course. So suppose that we let Z represent the amount of space in gigabytes that's consumed by programs on your phone. So if Z stands for that amount, I can use Z with the subscript of I, Z initial, to represent how much was initially consumed by programs on your phone, and Z with the subscript of F, Z final, the final value of Z, how much by the end of the described situation, how much space was consumed, measured in gigabytes. So the third variable here, this DZ, this symbol here, we're going to use a separate symbol for that, although we can define it in terms of the other two, right? Will be used to describe the change in the value of Z. So we're going to talk a little bit more next class period about what's meant by a variable, because as much as that seems like a word that you have used forever, sometimes people use it when they don't really mean variable. Just because it's a letter doesn't mean it's a variable. But something that varies, I can use a symbol. I use a letter symbol for it. Then that letter symbol, or whatever sort of symbol I'm using, can be called a variable. If it's representing something, a quantity that's varying, then a symbol to represent its value is a variable. So Z, the amount of space in gigabytes consumed by programs, I can call that a variable because it's something that, based on this description here, is clearly varying. It's not staying the same all the time. It's not the amount of space that there is on my phone altogether that could be used by programs. It's how much is used right now. Well, I have an initial value and a final value. So right now, which one am I talking about? We can talk about the change. We can talk about how much it was, how much it became. And from those two, how do you compute the change from the initial and the final? Anyone? Yeah, final minus initial. Z final, ZF minus ZI, Z initial, would tell me the amount of change. And regardless of which one of those two is larger, if you do final minus initial, you'll have a value for change that's signed to indicate in what way it changed. So in this case, if I do the computation final minus initial. Wait, what do we have here? I don't have final and initial. What do I have? 7.8 gigabytes of space. I see a number there. What variable or expression could be used for this 7.8? Yeah, your current programs take up 7.8 gigabytes of space, which that's kind of like current. Is that initial or final? Well, if we read the rest of this, then you download a new app that uses that. How much is used by programs now? So 7.8 was initial or final? Initial. All right, what's this 0.5 gigabytes? That's the change. So how would I find the final? Yeah, I could add them. The initial value plus the amount of change to get the final, which is just a algebraic rearrangement of exactly what we said before. If you need to calculate change, final minus initial. If you want to know what's the final, if you know the initial and the change, you add those. The initial plus the change, and a change could be negative, so adding the change could actually decrease the value. We want a positive change to indicate increase, and a negative change to indicate decrease. But we could write here that the initial value of z plus the change in z, dz, equals the final value using the symbols, or we could write using the numbers, 7.8 plus 0.5 gives me this final value, 8.3. So the point of this isn't, do you know that the answer is 8.3? The purpose of my showing you this isn't that, because I hope that that's something you could have figured out a long time ago. The point is to get ourselves a language that we can use together in terms of some expressions we can use to represent quantities that, in this case, we're changing from one to another, increasing from 7.8 up through an additional 0.5 gigabytes gives us a final value of 8.3. So apparently I have some letters that disappeared on me. I'm going to have to work on my resolution here. So let's see. So let me fill in the blanks here. Using notations that we had on the last one, z initial, z final, and dz, write an expression for blank and blank. Let's say at first 3 gigabytes of memory was used. After starting a new program, 5.5 gigabytes of memory was being used. What I'd like you to do, since we already have blanks in there, is what those two numbers there could be represented by symbols. Think about what those are, and then how they would be related to the missing quantity. So we've got 2 out of 3 quantities values up here. Assign symbols to both of them, using the same symbols we were just talking about. And then after that, if you can write an expression that relates the 3 that you have, any order that you want to, but maybe it would make sense, whatever's unmentioned, write that equals something with the other 2, or something with those 2 that we have, some sort of relationship between them equals the unmentioned quantity, the one that of initial, final, or change, the one that isn't those 2 numbers. The first question was space use. This was actually memory being used, but I don't really think of that. All right, so symbol-wise, 3 gigabytes of memory at first. 3 gigabytes of memory was used. What symbol might best represent this for the situation? Yeah, the initial. At first, that amount was used, zi, z initial. After starting a new program, 5.5 gigabytes of memory is being used. What might that best be represented by? Z final, zf, right? So if the missing one is dz, the change or variation in the values. So if I wanted to write dz equals, what symbols would I write afterward? Using the symbols. ZF minus ZI, yeah, final minus initial. If I wanted to compute a value for it, dz equals, yeah, 2.5 gigabytes. So the amount of memory used was 3, and then later it was 5.5. So that change that occurred, or the variation or the increase that happened, was that dz value that's in between. So we're just using this other symbol. It's an additional, it's something that changes. We can think about it, because did it suddenly, like it was 3 and then it was 5.5. Is that instant when you start a new program? Does it instantly go from 3, all of a sudden it's 5.5? Pretty fast, probably. But if I were to have half installed the program and then it hung up, there'd probably be all sorts of things going on. But I can imagine that I can start at this 3 gigabytes memory, and it goes to, by increasing, that dz starts at nothing's happened yet, and then, ooh, something's happened. And by the end, by the time that I'm talking about starting up this new program, dz is 2.5. But it took on all the different values between 0 and 2.5 in order to get to that point. dz is its own variable. We started increasing the amount of memory used, and then finished by the time the program was done opening. All right, so same general premise here, different situation. When you got your computer, 14 gigabytes of disk space was consumed by your operating system. You've added programs and files to take up an additional 40 gigabytes of disk space. So if we use the same letters, let's use Z for fun, Z's for fun, initial, final, and change in Z. Which of those three are we missing right now? Which isn't stated directly? Final, right. We have the initial value when you first got your computer, 14 gigabytes. So that's our Z initial. Then you added things. So it's an increase of 40 gigabytes. If I want to find that final, what computation with numbers do I do? Yeah, the 14 plus 40. What symbol operation would I do? Z initial plus DZ, yeah, the initial plus change. All right, so we get the idea on that. So if you're trying to compute a change, which change can be understood a lot of different ways. We'll talk about this as a specific portion of the book where we talk about all the different ways that we can mean change. But what we're talking about here is not just like, poof, we changed from one value, now it's a different value, like you changed clothes or something. We're changing by increasing from one value to another, or decreasing in other cases maybe from one value to another. So it's this idea of varying through a bunch of different values to get from a starting point to an ending point, that idea of change going on. So time elapsing or something like that. You can imagine just some continuous amount of variation happening. So this change that we've been computing, the dz, was the final minus initial, so z final minus z initial. If it was x, we could call x final minus x initial and dx. It doesn't matter what underlying variable symbol you're using to represent it. Just pick one. You can talk about initial, final, and change, and that same relationship is going to hold, where that change represents that difference or that amount of variation that's happened. So how much has gone by, if you want to think about it that way, or how much has disappeared, how much has accumulated, that change. So to move away from just talking about one quantity at a time, we're going to spend a bit of time just talking about the structure of functions and relationships between two variables, two changing quantities. When the change in one causes a change in another, or when two things change because of one another, such as, what did I mention earlier, driving down the road. If I tell you how fast I'm going, you could tell me how far. So as time goes on, if I'm driving, I'm going to have accumulated a distance driven. It's going to add up over time. I will have driven farther and farther the more time goes by. And so there's the time aspect and there's the distance aspect. And one is related to the other by a rate, but also, if I wanted to know where I am, I need to know where I started from. When I posed that before, there was no initial value, final value, just thinking about, in general, this distance. But in any case, when we have two quantities that are related to one another, we can talk about how a change in one or how varying one impacts the size of the other or makes the other one also change or vary. So if y changes along with x in some relationship, we can be determining the change in y based on dx. And sometimes, if you have a linear relationship, it's something that you've done a lot. And maybe some questions will seem easy, but some will be harder. But talking about how one impacts the other and how knowing the amount of change in one can help us figure out the amount of change or variation in the other. We talk about that rate, like how fast are you driving? Velocity is a type of rate. Now we weren't talking about time when we were talking about installing programs on our computers before. We were just talking about the amount of memory. But if it took an amount of time for things to happen, maybe it wasn't the same rate all the time. Maybe it was slow at first, and then once it starts going, then it really gets going and installs fast. So the amount of memory used up, little, and then all of a sudden everything kicks into gear and it goes up quickly. Going up meaning more memory used or more space taken up, depending on which problem we were talking about. So this up and over and those sorts of things are very vague. We need to talk about what are the things that are going, what's up? More of something, more memory. More memory is being used because, well, as time went by, more memory was used because you were installing a program. Now, as I said, we didn't actually have any time element in those previous ones, but in reality, there is some time involved. That just isn't the aspect we were interested in. So, a constant rate of change, I mentioned this term earlier, and here's a distance and velocity sort of question. Driving in your car, once you get on the highway, your car's cruise control is set to a constant 70 miles per hour. All right, great. So, if I talk about what's the meaning of that constant rate of my distance changing 70 miles per hour, anyone have a way that you could describe what that tells you? Yeah. For every hour you go 70 miles. That is absolutely true. Is that all that it says? Like, what if I go for half an hour? Yeah, it's always a 71 hours to miles to hours. Yeah, ratio. So yeah, after 1 hour, you go 70 miles. After 2 hours, if you're still going at cruise control ahead and hitting traffic, 140 miles. After half an hour, 35 miles. But at any amount of time, no matter whether it's one additional hour or for any additional amount of time that we append on to how long we've traveled, the additional distance that you will have traveled during that interval is also going to change by an amount that's 70 times as much, keeping in mind the units we were talking about. So every additional hours would mean an additional 70 miles traveled, but we can expand that beyond just for individual amounts of time to be for any amount of time, for any additional time, for any additional time elapsed. If I multiply that by 70, I'll get the additional amount of distance driven during that time interval. And it'll be measured in miles, since the 70 was miles per hour. So if I measure the time in hours, multiplied by 70, I get the distance in miles. Now, I don't know where I started from. This isn't about where we started from and where we ended and how long it's going to take me to get someplace. This is just talking about what's the meaning of that 70 miles per hour, that rate. And so again, you can talk about it like a unit at a time, and that's a good starting place. Think, oh, 70 miles per hour, in an hour you go 70 miles. But any amount of time, and that's why there's, when you graph linear functions, it's not just dots every unit, you connect them all, because as x varies from 0 to 1 to 2 to 3 and hits all those infinitely many numbers in between, there are infinitely many y values. In this case, if maybe x is the time, y is the distance traveled. There's infinitely many different values that y takes on. And so the increase in the y is different every time. Now, it doesn't matter if I start from 0 for x or start from 15 for x or whatever this is. For any additional time traveled, regardless of what time of day it is or how long ago I started driving, if I'm still driving at 70 miles an hour, the increase in distance during that little increment of additional time is 70 times as much. Just keep in mind the units. So the distance is measured here in miles and the time in hours. So I believe this is what we talked about. There's a lot of different ways you could phrase that, but just make sure if you're trying to describe it in general that you, instead of using the example of one thing that matches up, if you want to describe it more generally, start from that example and then build out where does it go from there. So for any additional time traveled in hours, the distance increases by 70 times as much, and that distance is measured in miles. So you're filling up your gas tank and gas costs $2 per gallon. There's a different rate, doesn't involve any time. We've got $2 per gallon. So it's a constant rate. Luckily, as you're filling up your tank, if they kept changing the price on you, you'd be a little bit mad, especially if it was going up. So what's the meaning of this $2 per gallon, this constant rate? Think about what we just talked about a moment ago. Oh, it's 240? Oh, 245. Sorry, I was trying to remember what time we get out of here. Think about what we did last time with the 70 miles per hour. Start from a couple of basic relationships that you know you could compute, and then think about how do I extend that to in general to cover all situations. Again, that's kind of our goal. We're going to start from some specifics that we know and that are easy to understand, to visualize or compute, and then we're going to see how can I extend that to give me the full definition of this for all situations. So $2 per gallon. I wish gas were $2 per gallon. It is not. Well, if I buy a gallon of gas, how much does it cost? $2. If I buy 5 gallons of gas, $10. I just multiply by 2. So suppose I've been filling up my gas tank for a while. Right now it's at 11.273 gallons have gone into my tank. If I buy another half gallon, how much more is it going to cost me? $1. It doesn't matter that it was at 11 point whatever. That was a value of the total number of gallons of gas in my tank. We're concerned about how much more we're buying here. That's what my question was about. So if I buy dx additional gallons of gas and I have x gallons already in my tank, whatever it might be, I have a gallons of gas in my tank, and I buy dx more gallons of gas, how would I figure out how much more I have to pay for those dx gallons of gas? 2dx, right? Or whatever I'm starting from, if I let the number of gallons of gas increase by any amount dx, the increase in my price, not the total for all of the gas that I've bought, but the increase in my price is going to be $2 per gallon, so 2 times that dx. The change in for any additional gas purchased, the extra cost, the change in the cost, the additional cost, the variation in the cost, 30 different ways I could say this, is going to be 2 times the amount of additional gas purchased. So as I let the gas flow a little bit longer, however much that is in gallons, multiply it by 2 to get the variation in my cost, which would be an increase in my cost in this case. We can have negative rates of change. We're going to talk about that next time. But for today, we'll stop at this. We'll pick up next time. So I will see you Tuesday, but some of you will see your recitation instructor on Monday. You all have homework due on Monday night. I will put more people into Math AS as soon as I get back to my office after this. Thank you very much.
Me? Yeah.